Hi everybody, I'm going to walk you through explanations for the Castlelearning assignment on kinetics and equilibrium. This is a screen recording, so I'm trying to do this all in one shot. Okay, so the first question, when a substance was dissolved in water, the temperature of the water increased. This is described as blah. So all of the answer choices have to do with endo or exothermic and what that means for energy. So what I would do first is eliminate the ones where the definition doesn't match the term. So endothermic is not the release of energy, and exothermic is not the absorption of energy. So that gives you like a 50-50 right there. So think of this, so here's the substance, then I'm dissolving it in the water. And the temperature of the water is going to go up when the substance dissolves. So that means that there's got to be energy transferred, because energy goes from high to low. There's got to be energy transferred from the substance to the water. Okay, so if energy is leaving the substance, that means it's getting released, which means you're talking about an exothermic reaction. Which diagram represents an exothermic reaction? So you're never going to see a reaction where the starting and ending energies are the same, and this doesn't even make sense. Exothermic reactions are a release of energy, which means the products have less energy than the reactants. So the end has less energy than the beginning. So that gives you choice 2. Number 3, which change of phase is exothermic? You want to have a release of energy. Now looking at all of these, they're all phase changes, right? It's the same substance on the left side and right side, it's just the phase that is changing. So what I always do is, okay, in one direction to go from a solid to a liquid to a gas, that's an absorption of energy. Gas to liquid to a solid is a release of energy. So now look at these answer choices and see which one goes in the exothermic direction. Solid to gas, that's going, based on my little diagram, that's going from left to right, so that's endo. Solid to liquid is also going from left to right. Gas to liquid is going the opposite direction, and then liquid to gas. So for a question like this, you always pick the phase change that's going in the opposite direction. Number 4, given this reaction, it occurs more rapidly when the 10-gram sample of magnesium is powdered rather than in one piece, because powdered magnesium has, okay, so anytime you're talking about a solid chunk versus a powder, you're talking about surface area. A powder has more surface area than one chunk of a substance. Number 5, adding a catalyst to a reaction will do what? Okay, so if you think about a catalyst in terms of what it does in a potential energy diagram, a catalyst will give it a shortcut. So there's the original amount of energy needed to get the reaction started is that green arrow that I just drew. That's the original activation energy. If I add a catalyst, instead of having to go all the way to the top of the hill, I just have to go to the top of where the catalyst energy is. So it lowers the amount of activation energy that's needed. Choice 2 and choice 4 are wrong because it's saying that it's changing where the starting point is. You're not changing where the starting point is, you're just giving a shortcut in the middle. Okay, so if I'm trying to travel from point A to point B, a catalyst just gives me a quicker route to get there. It doesn't change where I'm starting. Number 6, here's a Le Chatelier's question. In which reaction will the equilibrium shift to the left when the pressure is increased? Okay, so the rule for pressure changes is if the pressure increases, I shift to the side where there's less moles of gas. So I want the reaction to shift to the left when the pressure is increasing. So I want the left-hand side to have fewer gases than the right-hand side. So look at where your gases are in this equation. Okay, so for reaction 1, I have 1 mole of gas on the left and 1 mole of gas on the right. So a pressure change isn't going to do anything. For equation 2, I have 1 mole of gas on the right and 0 moles of gas on the left. For equation 3, I have 1 on the left and 0 on the right. And for equation 4, I have a total of 3 moles of gas on the left and 2 moles of gas on the right. So if I wanted to shift to the left when the pressure increases, I want fewer moles of gas on the left-hand side than on the right-hand side, so that gives me choice 2. Number 7, reaction of hydrogen and oxygen to form water is best described as what type and then what's going on with the energy. So again, you can eliminate the ones where the definition doesn't match the term. And then you would have to, this was a table I question. There's no way that you're supposed to memorize something like this, okay? So anytime you're talking about a reaction with energy and it doesn't explicitly tell you to go to table I, a lot of times they do, But if it talks about some sort of process and energy and there's no diagram and there's no like equation with the energy written in, you would go to table I and look it up. I'm fairly certain it's an exothermic reaction. I don't have table I in front of me right now, but that's how you would get that question. Number 8, when a single 1 gram piece of zinc is added to 3 molar hydrochloric acid, the reaction is slow. Which procedure would increase the rate of the reaction if the reaction were repeated? So here's all the things that, like all the factors that I'm dealing with. A 1 gram piece of zinc, a 3 molar acid, and 25 degrees. So there's lots of things that I could change in this to speed it up. So look at these answer choices. Using 1 gram of powdered zinc, using 1 molar hydrochloric acid, so that's decreasing the concentration. Choice 1 would be increasing the surface area. Choice 3, that's decreasing the temperature. And 4, decreasing the concentration of the zinc. If it's a solid piece of zinc, decreasing the concentration would just be decreasing the amount of the zinc that we have. So which of these things would make it go faster would be choice 1. Number 9, what effect does the addition of a catalyst have on a chemical reaction at equilibrium? So from the Le Chatelier stuff, if I add a catalyst to a reaction that's at equilibrium, it's not going to disrupt the system. It's just going to let it establish equilibrium faster because it increases both of the forward and reverse reaction rates. Number 10, potential energy diagram of reaction is shown. So there's different things you could look at here. First of all, we would say that this is an exothermic reaction. The question is asking for the heat of reaction. Heat of reaction is delta H, the change from start to finish. So here's the start, here's the finish. The lettered interval that represents the difference between my starting point and my ending point is interval B. Number 11, this reaction goes to completion. So this is not a reversible process. I have these two solutions that I mix together. It's a double replacement reaction, right? And I get a solution that forms because sodium nitrate is soluble, and then I get this solid precipitate that forms. That's why you can't reverse it. The barium and the sulfate are bonded together so tightly that you can't rip them apart to reverse the process. Number 12, when this reaction reaches a state of equilibrium, the concentrations of the reactants, this would become constant. And you saw this in the lab activity that I had you do with the graph, that your graph ended up looking like this. At this point, they established equilibrium. And it's not because this was our reactant amount getting smaller and our product amount getting bigger. They didn't come together and match. Okay, it's possible that a reaction could end like this, that could reach equilibrium where the amounts are the same at the beginning for the reactants and the products, but they don't have to be. It's the fact that they remained constant. There's no change. So this would be concentration on the y-axis, or in your case with that graph activity, it was volumes. The volumes weren't the same, right? This volume and this volume are not the same, but they were constant, okay? So concentration, concentrations are constant at equilibrium. The rates of the forward and reverse reactions are equal. A piece of magnesium ribbon is held in a Bunsen burner flame and begins to burn according to this equation. We did this in the lab where you lit the magnesium ribbon, it was bright white, and I told you not to. Oh, remember when we were together in lab? It was bright white, and I was like, don't stare at it, it's bright white. So all of you were like, we're going to stare at it. So why does this reaction begin? Well, because the magnesium is not going to set itself on fire. So why did the reaction start? It's because the reactants, which was the magnesium ribbon and the oxygen, are activated by the Bunsen burner flame. The Bunsen burner flame supplied enough energy to overcome that barrier of activation energy. So here's the magnesium ribbon and the oxygen. That's how much energy they had at room temperature. That wasn't enough energy to get them going. So heating them up in the burner flame gave them more energy, let them hit that activated complex, and then go through the rest of the reaction. Number 14, solution equilibrium is reached in the system. Okay, so solution equilibrium is when you have a saturated solution. Saturated solution is when you have the rate of dissolving and the rate of crystallization are equal. This is a kind of a crappy worded question. I don't really like it, but the rates of dissolving and crystallization would be equal and not equal and greater than 0, which means you do have motion occurring. You have dissolving and crystallization happening. 15, which reaction results in an increase in the entropy of a system? Entropy is randomness or disorder. So I want my particles to become more disordered as the reaction takes place. So gas to liquid, think about look at the phases here. If I have a gas that's all crazy and all over the place and I turn it into a liquid, which is more organized, that would not work. If I had a liquid and changed it into a solid, which is very organized, that would be a decrease in entropy. Then choices 3 and 4, we have liquid changing into multiple gases, or choice 4, we have gases changing into a liquid. So that leaves us with choice 3. Number 16, which interval represents the activation energy of the forward reaction? So activation energy is a hill that you have to climb from where you start. The forward reaction tells me I'm starting to the left-hand side. So the activation energy is this hill, which is represented by interval C. 17, this was the last lesson of this unit. A reaction must be spontaneous. Okay, so spontaneous is straight memorization. You have to release energy and you have to get more crazy. That's memorization. Number 18, what's the minimum amount of energy required to initiate the forward reaction? So initiate means I want to get it going, and forward means I'm starting on the left. So the amount of energy to get this reaction to start is going to be this much, which is 30 kilocalories. It's the difference between where I start and my peak. Number 19, the change that will shift the equilibrium to the right. So I want this to happen. Okay, so keep in mind we have these mnemonic devices to help us. So if I want to shift it to the right, adding a catalyst won't do it because catalyst will speed both reactions up. Adding more oxygen. Well, if I add more oxygen, that's CIA, that would shift it to the right. So there's my answer. Decreasing the pressure would shift it to the side where there's more gases, which is the left-hand side. And increasing the temperature would also shift it to the left. Number 20, okay, pressure increased. So we have to count moles of gas. So there's 4 moles of gas total on the left and 2 moles of gas total on the right. So if I increase the pressure, it's going to shift it to the right. So if it shifts it to the right, it's saying it's going to increase what? Well, if I shift to the right, whatever I'm pointing at with my arrow is going to go up. So the ammonia is going to go up. 21, if a catalyst is added to a system at equilibrium, the temperature and pressure are constant, there will be no effect on the heat of the reaction. Both of these will both increase. So both will speed up. It's going to decrease the activation energy, but it's not going to change the heat of the reaction or the delta H because the starting point and the ending point aren't going to change when I add a catalyst. It's just the route that I take in between. Number 22, a solution in which the crystallizing rate equals the dissolving rate. This is a solution equilibrium. The saturated solution's at equilibrium. 23, increasing the nitrogen would increase the forward reaction due to what? All right, if you're talking about increasing a reaction rate, it's because there's more effective collisions. Okay, the only thing that's going to change, well, nothing's going to increase activation energy. The only thing that's going to decrease activation energy is a catalyst. And a decrease in collisions would slow it down. 24 is a CIA problem. We're increasing the concentration of nitrogen. So let's follow like the chain of thought here. That would shift it to the right, which would cause the NO to go up. It would cause the oxygen, which it's asking about, to go down. 25, when a catalyst is added to the reaction, it'll change what value? So drawing your catalyst, what does it change? It changes anything that once hit the top. So it's going to change 2 and 3. It's not going to change 1 because that's the energy that I started with, and it's not going to change 4 because that's the energy that I end with. It's just going to change the stuff in between. 26, given this reaction at constant pressure, when the temperature is increased, so here's a TIA question. Here's my heat. I'm going to increase my heat. It'll shift to the right, which means H and Br would go up and HBr would go down. So it would shift to the right, and it's asking about HBr. The HBr would go down. 27, what's the overall result when methane burns? This reaction is also on table I, so you could look it up. But also the fact that it's saying burning, that's combusting. So combustion, does combustion absorb energy or release energy? It gives off energy. It's releasing it. And if you release energy, you're exothermic. The sign of an exothermic reaction is negative. So, but table I could also tell you all that stuff. 28, which change would shift the equilibrium to the right? So I want it to go to the right. So let's think of things I could do to this reaction to change it. If I increase the temperature, that's TIA. If I increase this temperature, it would shift it to the left. So that's not it. If I increase the pressure, it will shift it to the side that has less moles of gas. So here's 3 moles of gas on the left, 2 moles of gas on the right. So yeah, that would shift it to the right. Decreasing the SO2 would shift it to the left, and decreasing the amount of oxygen would also shift it to the left. Number 29, what change would not affect the concentrations of A, blah, blah, blah? A catalyst. All of these other things, that's CIA, that's TIA, that's PIL, those will all cause a shift, but adding a catalyst will not. What would be a result of an increase in temperature? So this is TIA. So here's my heat. If this goes up, I would shift to the right. So that eliminates choices 1 and 2. And what happens to NO2 when I shift to the right? Well, the arrow is now pointing towards the NO2, so it's going to go up. Why? Because the forward reaction is making more NO2. Number 31, as liquid water is added to form a solution. So if I have this solid potassium nitrate and I add water to it and it dissolves, so the solid potassium nitrate was all nice and organized and I add water to it. Well, what happens to something when I dissolve it? The particles spread out, so the entropy is going to increase. 32, what would cause an immediate increase in the rate of the forward reaction? So I want this to go forward, so I have to think what's going to happen. Increasing the NO would shift it to the left, so that's not it. Increasing the nitrogen on the left would shift it to the right, so there's my answer. Decreasing the temperature would shift it to the left, and decreasing the pressure would have no effect because there's an equal number of moles of gas on each side. Which change would result in a decrease in the amount of NO formed. So I want that to go down. So that means the reaction has to be facing the opposite direction. So what's going to cause my reaction to shift to the left? Pressure change won't affect anything because there's the same number of gas particles on each side. Decreasing the nitrogen would shift it to the left because you're looking to replace it by reversing the reaction. 34, what occurs when hydrogen is increased? So CIA, this goes up, I shift to the right. NH3 will go up, N2 will go down. So rate of the forward reaction will increase, and the N2 will decrease. That's choice 1. And finally, which interval in the diagram represents the difference between the products and the reactants? Well, here's my products, here's my reactants. So that's how much energy they have. The difference between them would be interval 4. So there's your Castlelearning explanations. I know this is completely crazy right now, but I hope you got some understanding of these concepts in the kinetics and equilibrium unit. We're going to be looking at some nuclear chemistry stuff next, so I'll be pushing some information out to you then. Bye.